All right, babies, welcome to a brand new chapter. In this short little chapter we're going to look at what are called similar figures. Similar means that things are going to be the same shape. They're going to look identical, but they are not going to be the same size. So what we're going to do within this chapter is look at and investigate properties of similarity. To kind of introduce the idea of similar shapes or similar figures, in this section, we're going to focus on what's called a dilation. So a dilation is a special type of what's called a transformation. A transformation means a change. So it's when we take one shape and make a change to it to get a new shape. Specifically, a dilation is when we are going to take a shape and make an enlargement, okay, or we are going to make what's called a reduction. So an enlargement means we're going to make it bigger, and a reduction means we're going to make it smaller. And we're always going to do this around some fixed point. So for example, you have here shown triangle PQR shown here. And let's say that I make a dilation. What I'm going to do is I'm going to take that shape and I'm going to make it, let's say in this case, an enlargement. So I would have here P, Q, and R, but you'll notice labeled differently. We have P with an apostrophe, Q with an apostrophe, and R with an apostrophe. When I see that apostrophe, like for example, P with the apostrophe, this is called P prime. So prime is our way of showing the changed object, okay? This is what's called the image, okay, of our original object. So the blue would be our original, and the red shape would be our image. And you'll see it's labeled with the same 3 points, P, Q, and R. We just use that apostrophe. So what we're going to talk about is how to make a dilation, whether we're making an enlargement where something is getting bigger or a reduction where it's getting smaller. In order to do this, an enlargement or a reduction, a dilation in general, is found or is done by using what's called a scale factor. So a scale factor, which you're sometimes going to see labeled as K, is a ratio of the length. It is simply, another way to think about this is a multiplier. So it's going to be a multiplier, it's going to make it bigger, okay? Or it could possibly make it smaller. So the two types of dilations we see are an enlargement or a reduction. So an enlargement is going to be anytime our scale factor is greater than 1. So for example, if I have a scale factor, say K equals 2, what that means is my entire shape is going to be doubled. Whereas a reduction is going to be anytime I have a scale factor less than 1. So for example, if I have a K value equal to 1/2. So instead of being doubled, we would see here that it's cut in half. All right, so anytime we make a dilation, all it is going to be is just simply taking a scale factor and multiplying those sides or whatever it might be by that scale factor to get our new image. So our first example, what we're going to do is we're going to try and find the scale factor of the dilation being made. So notice here that I have a paper clip, okay? Paper clip we have labeled P. Now, all dilations are made by some center point. So let's say that this dilation is made from point C. Okay, and you'll see that you have these two lines kind of drawn out here showing the expansion where my paper clip, I have the small paper clip, and obviously we're making the paper clip bigger, shown here by P prime. Okay, so in this case we're looking at an enlargement, and what I want to do is I want to find the scale factor. So to find the scale factor, what we're going to do is we're going to take, in this case, we're going to take our image length, which is P prime, and we're going to divide it by the original length, which is just P. So if I want to find the scale factor here, my image length is going to be 12 units, and my original length is 8 units. So to find the scale factor, I'm going to take 12 and divide it by 8, which would give me a scale factor of 1.5. Okay, which means that this paper clip is 1.5 times larger than the smaller paper clip. We can do the same thing here. Now in this case, notice P, that's my original object, and P prime is my image. Here we're going to have the opposite, which is a reduction. Whoopsie daisies. So for a reduction, Anytime we want to find the scale factor, we're going to take that p prime and divide it by p. So for a reduction, here's what we're going to see. Our image distance is 18, and our original distance is 30. So notice here how this is a little bit different. For a reduction, we're going to see, instead of our numerator being the larger number, we're going to see our denominator being the larger of the numbers. So if I were to divide these two out, I would get a scale factor of 0.6. So anytime you have an enlargement, notice my scale factor is going to be bigger than 1. 1.5 is bigger than 1. And for reduction, my scale factor is going to be less than 1. So in this case, 0.6 is less than 1. Now what we're going to do is we're going to look at how does this affect shapes on a coordinate plane. So if I were to make any sort of dilation using points on a coordinate plane, so points of x and y, all I'm simply going to do is I'm going to take, so let's say that I have a point of, say, point P is 2, 2, and let's say that my dilation, my scale factor is going to be 2. What I'm going to do to find P prime is I'm simply going to take my coordinates of x and y for P, and I'm going to multiply everything by 2. So what I'm going to do is I'm going to take the x value 2, and I'm going to multiply it by 2, and I'm going to do the same thing for the y. I'm going to take 2 and multiply it by the y value, which is 2. What I would get then is I'm going to get my image location to be at 4, 4. I would do the same thing if my k value was less than 1. So when we find the coordinates of our new image, if we're using a coordinate plane, all we're going to do is take that scale factor and multiply it by the x and y of each point of our object. So in our first example here, using this idea of the coordinate planes, we have our triangle A, B, and C. And what we're going to do is we're going to dilate this by a scale factor of 2. Okay, so scale factor of 2. Since 2 is bigger than 1, what's going to happen here is we're going to see that this is going to be an enlargement. But here's what we're going to do. We're going to take all three of our points, starting with A at 2, 1. We're going to take all three of these points and simply double everything. If our scale factor is 2, we're going to double it, and that's going to give us our new location labeled A prime. So if I double 2 and 1, I would get 4 and 2. The reason why is because 2 times 2 is 4, and 1 times 2 is 2. And I'm going to do this for each point. So B, which has coordinates of 4, 1, again, I'm going to multiply by 2, and that will give me my new location, B prime, which would be 8, 2. And the same thing with C, which have coordinates of 4, -1. I'm going to double those coordinates, and that's going to give me my new location for C, again, C prime, which would be at 8, -2. And then our goal is just simply to plot those 3 points, which I'll do here in green. And you'll notice that what I get is a larger triangle, okay? And you'll notice that this triangle looks almost identical to this triangle, right? A prime, B prime, C prime looks very similar to A, B, and C. The only difference is that it is now larger. So we made an enlargement by just simply taking the coordinates and multiplying it by that scale factor. Let's do the same thing here. Now we're going to have a quadrilateral, so 4 points. And what we're going to do is we're going to dilate it by a scale factor of 1/3. So 1/3 being less than 1 means that we are going to see a reduction. So let's start off first by plotting our 4 points, K, L, M, and N. Now our goal is to make a dilation by a scale factor of 1/3. So if our scale factor is 1/3, we're going to take each of these 4 points, K, L, M, and N, and we're going to multiply it by 1/3. So that means I'm going to take within each coordinate, I'm going to take each x and y and multiply it by that scale factor, and that's going to give me my new points called my image of K prime, L prime, N prime, and N prime. And what I will get here is -1, 2 for K prime, 0, 2, 1, 1, and -1, -1 for my image location. And then I'll show it here in red, plotting those 4 new points. I'll get my image, which will be the dilation of that original shape. And then look at that. Isn't he cute? That is the quadrilateral K prime, L prime, M prime, and M prime. Looks the same shape as our original object. The only difference now is that it is a third. It is 1/3 times smaller than what it was originally. All right, so last one here, if we were to try this again, we have triangle F, G, and H, and now we're going to do a negative 1/2 is our scale factor. So the only difference here is you'll notice that is a negative scale factor. So let's think about what's going to happen here when we throw that in. First thing we want to do is plot these 3 points, F, G, and H. Then the next thing I want to do is, once I have my triangle drawn, I'm going to take my 3 points F, G, and H, and I'm going to multiply all 3 of those points by my scale factor, which is negative 1/2. And that's then going to give us our new points, our image location, which is going to be F prime, G prime, and H prime, which I then get as 2, 1, 1, -2, and 1, 1. A couple things to notice here is you'll see again the 1/2, you'll see that all the values are cut in half. So 4 becomes a 2, 2 becomes a 1, and so on and so on. Now, what does the negative do? Notice my scale factor here is negative. The negative is going to change the sign of all our values. So a negative value would become positive, and any positive value would become negative. So when I plot those 3 new points, which I'll show here in blue, we're going to get our new image, F prime, G prime, and H prime. And you'll notice here that not only does it become smaller, so notice we have a smaller shape, but you will also see that where the triangle is once right side up as we look at it, you'll see that it's now upside down. So it was cut in half, but what the negative symbol made it do was also flip upside down too. Okay, so anytime we have a scale factor that's negative, we're going to see kind of a combination of 2 things going on here. But we still see the dilation of getting smaller, but that negative is going to change that shape and kind of flip it upside down. So in these 3 examples, just went through how to use that coordinate rule for any sort of dilation, which again, you're just multiplying by whatever that scale factor, whether it's greater than 1 or less than 1. Okay, last 2 examples here, we are going to use this idea of a dilation in a real life sense. So this is probably seen in many different examples, but here we're going to use what's called a magnifying glass. Okay, so a magnifying glass, as you guys probably have seen at some point in your life, would be an object that allows us to magnify something. So if I were to take, let's say, a magnifying glass and hold it over this spider, now it doesn't really do it here, but normally what a magnifying glass does is it makes an object larger. So this would be an example of an enlargement. So here you are given the original length, I'll call this P, and what I want to know is, given that a magnifying glass is going to enlarge something 6 times the object's actual size, I want to know what would be the new size of that spider. So all we're going to do is that if we know the original length to find, if I know my scale factor again is going to be 6 times, to find the new length, all I'm going to do is take that original length and multiply it by my scale factor of 6, which would give us a new length of 9 centimeters. And that would be, folks, a big spider. So this is an example of when you use this idea of dilations in a real life sense using a magnifying glass. Okay, another example of a dilation in real life would be the application of a reduction. So one of my favorite things from my childhood is action figures. So let's say that I had my man, Hulk Hogan, who stands approximately 6 feet 6 inches tall. So he's 6'6". Okay, now when I was a kid, I used to collect action figures. So here's an action figure of this very same Mr. Hulk Hogan. Obviously, an action figure is a scaled down version of the actual person. And what they try to do is they try and keep everything kind of proportional. So whatever his height is, whatever the circumference of his pythons, whatever it might be, they try and keep things consistent. So if the Hulk Hogan action figure is 6 inches tall and the real life Hulk Hogan is 6 feet 6 inches tall, I want to know what is the scale factor that we use to make this action figure. Okay, so this goes back to, think about here, shape of this action figure, I'll call this P prime, or the height, okay, is 6 inches tall. Whereas the real Hulk Hogan, standing from here all the way down, is 6 feet 6 inches tall. So again, as we do this to find the scale factor, what we're doing is we're comparing the original object, I'll call that P, to the scaled down version, which in this case is the action figure P prime. Anytime we want to find our scale factor, we're going to take our image length, or height in this case, and we're going to divide it by our original. So we know right now that the image, which is our action figure, is 6 inches tall. Okay, we're going to compare that to the original height of Mr. Hulk Hogan. But here's the thing, when I give you the original height, notice I give you 6 foot 6 inches tall. So that is combining feet and inches. So 6 feet and 6 inches tall. What I need to do is I need to change this into how many inches would the real Hulk Hogan be. So here's what we're going to know. We should know that 1 foot is equivalent to 12 inches. So if I have 6 feet here, that's going to be equivalent to 72 inches. How did I get that? I just multiply 6 times 12, but then I have to take into account that he is an additional 6 inches, so that would put his overall height at 78 inches tall. So what we're going to do is compare the action figure height of 6 inches to the real height of 78 inches. So again, when we do this, we got to make sure that what we are measuring corresponds to each other in terms of like the units that we're using. And all I got to do is then plug it into a calculator, and now I'm going to write the fraction form of it, but what I get is 1/13, which means that the action figure is going to be 1/13 of the actual size of Hulk Hogan. All right, so again, in this section, we looked at what's called a dilation. The two special types of dilations are enlargements and reductions, and it's all about using that scale factor. So again, if you guys got any questions, jot those things down. Good luck on the practice problems, and we'll see you next section.